First one is A into Bx is equal to AB into X. Second one, A plus B into X is equal to AX plus BX. Third one, A into X plus Y is AX plus Y, AX plus AY. Fourth one is 1 into X is X, where 1 is the multiplicative identity in R. See, more or less commutative algebra and linear algebra, just if you know the concepts of basic concepts of algebra, then commutative algebra will be more easier for you. So just like how we define a vector space, like that in algebra, we define modules. What do you mean by a module? R is a ring and an abelian group M plus is said to be a left R module if there is a scalar multiplication or there is a mapping A comma X to AX of R by M2, because R cross R by M contains all the ordered pairs. That means, suppose if you, how you define f of 2 comma 3 as 2 into 3, 6, like that. If there is a mapping, scalar multiplication, which satisfies for all X comma Y belongs to, for all X comma Y belongs to M, we are saying that an abelian group M plus, abelian group M plus is said to be a left R module if you have A into Bx is equal to AB into X, A plus B into X is equal to AX plus BX, A into X plus Y is equal to AX plus AY, and 1 into X is equal to X. Okay, so this is the elementary, what we call R module, a left R module. See, you can define in place of R by M, you can take M by R also. And also you will have XA into B equal to X into AB, or X into A plus B is in that way, right? In the other way also you can define R module. Okay, so immediate consequence after defining the properties of R modules are theorem. Let capital R be a ring and capital M is an R module. R module. Then we have first one, you have 0 into X is 0. Second one, A into 0 is 0. Third one, A into X minus Y is AX minus AY. Fourth one, A minus B into X equal to AX minus BX. This we know how to prove this. And the next one, all these are the basic properties. And next theorem is, let M plus be any abelian group and Z be the ring of integers. Ring of integers. Then we define nx equal to 0 if n equal to 0, which is equal to n minus 1 into x plus x if n greater than 0, which is equal to minus n into minus x if n less than 0. If you define nx, then M is a R module with respect to the above defined map, okay, which you can prove very easily. Just to focus on the definitions of R modules. And because we know, suppose if you define the set of all polynomials over ring R, Rx, if you take Rx is nothing but A naught plus A1x plus A2x square plus and so on plus an x power n. This is ring of all polynomials. Okay. So if you define, you can define Rx as R module with respect to addition of f of x plus y is equal to f of x plus f of y, and a into f of x is equal to, how you define two polynomials, sum of the polynomials, and sum a into f of x is equal to a into a naught plus a into a1x plus and so on plus a into an x bar n. So with this respect to this operation, you can define, you can say that Rx is a R module. Now, suppose let capital R be any ring, capital R be any ring, and M an R module. Then we say that M is said to be R algebra. M is said to be R algebra if there is another, binary operation, on M such that M plus dot is a ring. M plus dot is a ring. Okay, satisfying the property A into xy is equal to ax into y, which is the same as x into ay for every a belongs to R and x comma y belongs to M. In such case, we say that M is said to be R algebra. M, okay, so here, so this is about modules. Let R be a ring and M is an R module. A subgroup N of M plus is said to be R submodule if it satisfies the closure property. So what do you mean by submodule? Submodule is a subgroup. We know that if you say that M is R module, M is R module means you have M plus is an abelian group. So you can have a subgroup N of M is said to be a submodule if AX belongs to N for all A belongs to R and X belongs to N. Then in such case, we call it as a submodule. And also we say that you can prove if and only if condition. We say that M is an R module and N is any non-empty subset of M. Then you have N is R submodule if and only if AX plus BY belongs to M for every A comma B belongs to R and X comma Y belongs to N. As usual, you know how to prove it as a subgroup. And also we know the smallest subgroup generated by. So generally, how you define submodules like subgroups and all, you have submodules. Next definition is let. Students, always you focus on definitions, and while proving the theorem, you focus on two things. What is given, what you have to prove. Then you will get how to prove. How you define definition. Let capital M be an R module. M be an R module and SC is a subset of M. SC is a subset of M. Then smallest subspace generated by SC is the set of all intersection of all submodules N such that N is R module and S is subset of N. This is known as submodule generated by S. First of all, N is an R module, S is the subset of M. Okay, and S is any subset of M. Then we say that submodule generated by S. And we can see that this S is the linear combination of elements. Next theorem is let capital M be an R module. Let capital M be R module and the empty set not equal to S, which is the subset of M. Then the smallest submodule generated by S can also be expressed as sigma I is equal to 1 to N AI xi for N greater than 0. Each AI belongs to R and xi belongs to S. That is, you can write it as linear combination of elements of R and S. This we have seen, the smallest subspace generated by S even in vector space also. So just today we will focus on all the definitions which we are going to use in coming theorems. Then next definition, let capital M be an R module. Let capital M be an R module. Then for any ideal I of R, and any R submodule capital N of M, you have I into N is the set of all sigma I is equal to 1 to N I equal to 1 to N AI xi such that N greater than 0, AI belongs to I, xi belongs to N. So what you say, In is called the product of I and N. Okay, and for any submodules, see here, next one is second one. See, these are all the notations for any submodules. N and K of M, we have extension NK is defined as set of all A belongs to R such that AK is subset of N. AK is subset of N. So if you define this here, NK is not a submodule, but it is an ideal. It can be an ideal of R. So now suppose in place of N, if you take the element 0 such that 0K is equal to the set of all A belongs to R such that AK is 0 is nothing but the set of all A belongs to R such that AX equal to 0 for all X belongs to K. This is okay. So this is known as annihilator ideal of K, called the annihilator ideal. Of K. So which we denote by ANN, K, annihilator of K. Now, like that, let us define next concept, quotient modules. What do you mean by quotient modules? Let M be a module over a ring. Capital M be a module over a ring R. A binary relation theta on M is said to be a congruence on M if first one, a binary relation theta is said to be congruence if theta is an equivalence relation. Theta is an equivalence relation on M. And second one, x comma y and u comma v belongs to theta implies x plus u comma y plus v belongs to theta. Okay. And third one, x comma y belongs to theta implies ax comma ay belongs to theta for all a belongs to R. So this is known as congruence on M. Students, after finding these modules, we have to do going down theorem and going up theorem also. Tarvata 9 lemma is also important. We will do theorems on homomorphisms, homeomorphisms and isomorphisms also. First, let us understand the concept of congruence. Okay. Let capital M be a module over a ring R. A binary relation theta on M is said to be a congruence on M if first is theta is an equivalence relation on M. What do you mean by an equivalence relation? A relation is said to be an equivalence relation if it is reflexive, symmetric and transitive. Symmetric, reflexive and transitive. Then we say that it is a equivalence relation. Reflexive relation means you should have a comma a belongs to theta for all a belongs to M, and whenever AB belongs to theta, if BA also belongs to theta, then we say that theta is symmetric. Theta is symmetric and AB belongs to theta, BC belongs to theta, implies A comma C belongs to theta, then we say that theta is transitive. So, a binary relation theta on your module, M module over a ring R is said to be a congruence on M if theta is an equivalence relation, that is A comma A belongs to theta, whenever AB belongs to theta, BA belongs to theta, AB belongs to theta, BC belongs to theta, implies AC belongs to theta. So binary relation, all of you know, no? What is a binary relation? Which is a subset of A cross A. Now, here, x comma y and u comma v belongs to theta implies x plus u, that is corresponding elements are added. X plus u, y plus v belongs to theta. Again, xy belongs to theta implies ax, ay belongs to theta for all a comma a belongs to R. So in such case, we say that theta is a congruence on M. Now, next theorem is, let capital M be a module over ring. This is one important theorem. Learn this. Let capital M be a module over a ring R. Let capital M be a module over a ring R. For any R submodule, for any R submodule of N, sorry, for any R submodule N of M, the relation theta N defined by theta N equal to the set of all x comma y belongs to M by M cross M, such that x minus y belongs to N. Theta N is defined by, for all x, y belongs to M by M, you have x minus y belongs to N. Ante N is a subgroup with respect to addition. N is a subgroup, is a congruence. This is a congruence on M. This is a congruence on M. And conversely, whenever this is a congruence, and conversely, any congruence theta on M is of the form theta N for some R submodule capital N of M. In this case, what you will have, theta of 0 is N. Like we know, no? Suppose if you take R by S is a quotient ring, what is the 0 element of R? S only. So here also 0 element of N is, theta of 0 is N only. And theta X is X plus N for all X belongs to M. So students, to know the concepts of commutative algebra, one should be perfect with all the concepts of abstract algebra. Otherwise, you cannot learn this commutative algebra. First, focus on definitions. So you have seen what do you mean by a module, what is a submodule, and how you define this congruence. When theta is a congruence, it should be an equivalence relation, and xy comma uv belongs to theta implies x plus u comma y plus v belongs to theta. Whenever xy belongs to theta, ax comma ay belongs to theta for all a belongs to R. So based on this, what he says, he is asking to prove that theta n defined by xy belongs to M cross M, such that x minus y belongs to N is a congruence. Whenever this is a congruence, you have to prove N is a submodule, okay? Or any congruence theta on M is of the form theta N. This is clear congruence on M, trivial congruence on M. So to prove the theorem, I told you, no, you concentrate on two things. What is given? First, what we have to do, we prove that theta n defined by xc. First, suppose n is an R submodule. N is an R submodule of M. N is an R submodule of M. So then what we prove? We prove theta n defined by the set of all x comma y belongs to m by m such that x minus y belongs to n is a congruence on M. This is what you have to prove. Now you have, for any x belongs to M, you have x plus minus x, which is 0, belongs to n. So what do you mean? You can have x plus x belongs to theta n. So you have theta n is reflexive, proving that theta n is reflexive. Now consider if x comma y belongs to theta n, then you can write x minus y belongs to n. This implies minus of x minus y belongs to n, or this implies y minus x belongs to n. So this implies yx belongs to theta n. So you can have theta n is symmetric. Theta n is symmetric. Similarly, you have x minus y comma z belongs to theta n. Then always you can write x minus z as x minus y plus y minus z. Okay. So x minus y minus y minus z. So this belongs to theta n. Okay, because xy belongs to theta n means x minus y belongs to n. Y minus y comma z belongs to theta n means y minus z belongs to n. So you have x minus z belongs to theta n. So theta n is transitive. So you have theta n is symmetric. Sorry, theta n is an equivalence relation. Theta n is an equivalence relation. Now what you have to prove? You take two elements x comma y and u comma v in theta n. So tell me, what is x plus u minus y plus v? Sorry, y plus v, which is x minus y plus u minus v belongs to n. Therefore, you have x plus y, x plus u, comma y plus v belongs to theta n. And similarly, you have whenever x minus y belongs to n, ax minus ay, which is a into x minus y belongs to n, which implies ax comma ay belongs to theta n. Therefore, theta n is a congruence on M. So this is one important property. That is the reason I am focusing on this congruence. You consider from some R submodule n of M and relation theta n, how you are defining x minus y. So we are able to prove that it satisfies reflexive property and symmetric. Next, what we have to do? We will take that any congruence theta is of the form theta n for some R submodule n of M. So for this, see, conversely suppose we prove converse. Conversely suppose theta is any congruence. We prove that any congruence theta is of the form theta n. Any congruence on M. So put n is equal to theta of 0, which is the set of all x belongs to M, such that x comma 0 belongs to theta, like this. X comma y belongs to theta, which and only if x minus y belongs to n. Because see, you have x comma y belongs to theta means you can have y also belongs to theta. So that is the reason you will get x minus y belongs to n. This is if and only if x comma y belongs to theta n. So you can have theta equal to theta n. And also for any x belongs to M, we have y belongs to, sorry, for any x belongs to M, y belongs to theta x if and only if x comma y belongs to theta. This is if and only if x minus y belongs to n. Therefore, any congruence on R submodule M is of the form x minus y n. Or you can mention like this also. You write y belongs to x plus n. Okay, y belongs to x plus n also you can write. So what you have, hence you have theta x is equal to x plus n. So this is one important theorem from commutative algebra. X belongs to M. If you define, then you have for any, x plus n, comma y plus n belongs to M by n and A belongs to R. We have how you define addition of two modules x plus n plus y plus n. Okay, alpha into x plus n is alpha x plus n. So then you have M by n is an R module with respect to the above two operations. Okay, so if you define, this is called the quotient module of M by n. So the operations of addition and multiplication is known as quotient module of M by n. And the immediate consequence of this definition is, let capital M be capital N be or submodule of capital M. Then if you define K by N, where K is or submodule of M containing N, K containing N. such K by N is set of all X plus N, such that X belongs submodule of quotient module K by N. So K by N is the submodule of quotient module K by N. Let M be any we have discussed the product, no? IM is a subset of N, then M by N can be treated as R by I module by defining A plus I into X plus N is AX plus N. So like this, if it is known as R by I module. So how you define homomorphism? So already I gave, while giving introduction, we have discussed about homomorphisms. You know now what is you mean by ring homomorphism? Suppose R be a ring and M comma N be modules over R. So a mapping F from M to N. M and N are submodules over R. We define a homomorphism of X plus Y is equal to F of X plus F of Y. Then F of alpha X is equal to alpha into F of X for all alpha belongs to R and X belongs to M. So F of X plus Y is equal to F of X plus F of Y. We call it as a R homomorphism. Okay, R homomorphism. Whenever you are kernel of a homomorphism, it has set of all X belongs to M such that F of X equal to 0. The set of all those elements that are mapped onto 0 element. And the kernel is a submodule. We know that every homomorphic image of ring R is isomorphic to some quotient module. So in this you have fundamental theorem of homomorphism. What is the fundamental theorem of homomorphism says? Fundamental theorem of homomorphism. Fundamental theorem of homomorphism says that if F from M to N be an R homomorphism of R modules, then F of M is an R submodule of N. The quotient module, or you can say that M by F is isomorphic to F of M. This is the fundamental theorem of homomorphism, which we can prove easily with the knowledge of fundamental theorem of homomorphisms of rings we studied, and fundamental of homomorphisms for modules also. Now, let F from M to be an R homomorphism. Be an R homomorphism. R homomorphism of R modules. So, and K is kernel of F. And H is a mapping from M to M by K. It is a natural homomorphism. So then there exists unique homomorphism. Unique R homomorphism such that F equal to G circle H. F is equal to unique R homomorphism from M by K to N. G from M by K to N such that F is equal to G circle H. Now you have, see, you have M, N and this is M, N. M to N mapping is F. So you have M to M by K one mapping, N to M by K one mapping. Okay. If this is H and this is G, then you have F. So F is G circle H. So, and also whenever if G is a homomorphism, when this G will be a homomorphism, if and only if F is epimorphism. I told you onto homomorphism is known as epimorphism. And H is a isomorphism if and only if F is a monomorphism. A 1-1 homomorphism is a Now, next class, we will do projective modules and injective modules. Once you go through the concepts, what all we are expecting, just let me revise the concepts, what I have Today we discussed about elementary concepts in modules. What do you mean by a R module, left R module or simply a R module? That is satisfying the properties A into Bx is equal to AB into X, A plus B into X is equal to AX plus BX, A into X plus Y is equal to AX plus AY, 1 into X equal to X. So now immediate properties of module. In any module, you have 0 into X is 0, A into 0 is 0, A into X minus Y is AX minus AY, and A minus B into X is AX minus BX. So next, see, we can give many examples for our module. See, because R be any ring, M is an R module. When this R module will become R algebra, if it satisfies the additional property A into XY is equal to AX into Y and X equal to AY, which is equal to X into AY. And one more important concept is, which you have a combination of elements and quotient modules. Before going to quotient modules, you should be able to define a congruence. What do you mean by congruence on M? a binary relation, any relation, and a binary relation on a binary relation theta implies x plus u comma y plus v belongs to theta. Xy belongs to theta implies ax comma ay belongs to theta. And we have seen how to define a congruence or what is the general form of a congruence on submodules. Okay. With the set of all ordered pairs xy, for any xy belongs to M, you have x minus y belongs to n, and we proved that it is reflexive, symmetric, and transitive. And also we proved that x comma y, u comma v belongs to theta n implies x plus u comma y plus isomorphic image is isomorphic to some quotient group. Here also, if F is a mapping from M to N, is an R homomorphism. What do you mean by R homomorphism? You have f of x plus y is equal to f of x plus f of y, and f of alpha x equal to alpha into f of x. Then we say that it is a homomorphism. Now we will see f from M to N be R homomorphism. Kernel is K, and which is a mapping from M to M by K, and G is a mapping from M by K to N. You have F is equal to G circle H, and moreover, G is an epimorphism. Whenever G is an isomorphism, when F is an epimorphism, H is an isomorphism. If H discussed in today's class, in the next class, we discuss about injective modules and projective modules. Thank you.